Thank you for that very warm welcome. And I will start by, of course, apologizing that my presentation will be in English. Additionally, if the accent is a little strange too, although I live in San Diego, where Qualcomm, of course, is based, I'm actually from England originally. A country, of course, where we have warm and wonderful feelings for Luis Suarez, especially after the recent World Cup. So please forgive me for being also an inhabitant or an ex-inhabitant of also a country that was previously good at football too. Okay, so my presentation is entitled the 1000X Challenge, and this fits really very well with the previous two presentations by Eduardo and Thales in trying to address really the explosion of data, and specifically mobile data over the past number of years, and what we need to try to do to handle that explosion of data. Do we need to build networks that can carry this huge increase in capacity? What 1000X refers to is what Qualcomm perceives networks of the future will need to carry in terms of capacity based upon the current growth of data. Currently, we see nominally a doubling of the data capacity worldwide that networks need to carry. And if you extrapolate that over 10 years, that means that in 10 years' time, the networks will have to carry about 1,000 times the data that they carry today. So how can we do that? We can't continue to do what we do today. We have to change something, and so that's what we'll cover. A little bit about Qualcomm, just quickly, for those of you who don't know Qualcomm. Qualcomm, of course, was instrumental in the development, commercialization of mobile technologies. We've been around for about 30 years. For the initial CDMA-based devices that Qualcomm was responsible for introducing into the market, for the move from analog towards digital. So around for 29 years, continuing to innovate. It's a company that was founded by engineers and continues that innovation today with a huge focus on research and development and funneling the revenue back into more and more research. We're about 30,000 people strong, based in numerous places throughout the world, centers in San Diego. Talking about that model for innovation. And as we say, Qualcomm generates or innovates and then tries to feed those innovations into the wireless ecosystem. Eventually, Qualcomm and others commercialize those innovations. They end up in the hands of subscribers. That generates revenue that then feeds back into Qualcomm, and then Qualcomm invests a significant portion of that revenue back into doing more research and development to generate more products and more innovation. Deploying on a global scale the technologies, and this gives you some understanding of the amount of, or the impact that Qualcomm has had on the mobile ecosystem. In just 2013, you can see that there were more than 1 billion devices that were powered or enabled by Qualcomm technology, whether that's Qualcomm technology that's actually inside the device or Qualcomm innovations that were licensed to others and then developed into products. We have two significant business segments in Qualcomm. QCT, responsible for the semiconductors inside of a large number of the handsets in this room today, of course. We are number one in wireless semiconductor with the largest fabless semiconductor company. Since the company was founded in the mid-'80s, we've shipped something like 15 billion chipsets since the company was founded. Last year, in fiscal 13, nominally last year, we shipped about 716 million Qualcomm chipsets. That's the silicon that's inside of the devices, and then, of course, there's the technology licensing component as well, the patent portfolio that Qualcomm owns with significant licensees, not just in 3G, not just in CDMA-based technologies, but also in LTE as well. So we have a significant technology investment in both 3G as well as 4G moving forward. And there's our global R&D organization. As we said, we have a long history of invention, and this is driven by significant investments in research and development. If we look here from the initial investigation of TCP/IP type services over CDMA back in 1993, we can see how Qualcomm does feed that revenue, considerable amounts of that revenue back into research and development. Looking at 2013, approximately $5 billion that was fed back into R&D. And we can see the impact of this investment as we see the inventions and innovations that are introduced. The first 1 gigahertz mobile chip. Back here in 2007, I went too fast. The first Android smartphone was also a collaboration between Google and HTC back in 2008, 2009. And then the first integrated 3G LTE chipset back here in 2010. Okay, so a brief introduction to Qualcomm. Let's now talk about the mobile data challenges and how we address that 1000x challenge that we foresee. What is it driven by, predominantly? We notice that it's really not just phones now, it's tablets. It's the devices that are everywhere in our lives that are now connected some way to the internet, and we see that this will continue further and further. To give you some idea of the impact, as we use our devices for richer and richer content, and richer content really comes down predominantly to video. People are using their devices more and more now to watch videos. The screen sizes increases as tablets have been used and connected to the internet. So we can see that one estimate is 2/3 of mobile video traffic, or two-thirds of traffic, will be video by 2017. And we can see the impact of this on the network from downloading a simple song where we're looking at 0.14 gigabytes of data and that impact on the network, through to downloading a high-definition movie which would take about 6 gigabytes of data. A huge difference in the impact of the network by being able to do that. If lots and lots of people do that on lots of different devices. I guess 25 billion devices, somebody had mentioned that was 50 billion devices connected. So there's a factor of 50%, but it's still a huge number of devices compared to where we are today. And so that, I think, was a Cisco estimate of 25 billion by 2020. And the cumulative forecast between 2014 and 2018 was about 8 billion smartphones. 8 billion smartphones that are all doing these types of activities. And so therefore, this is why we need networks that carry much more capacity than they do now. Okay, so one way we can address this need is by really changing the way we design our networks. Eduardo's presentation before lunch showed the classic hexagonal grid layout for designing cells, and this is where we all started. This is where we started 20 years ago designing cells. And the capacity of a cell is reached, and then you split the cell into 3 additional cells, and you continue that process as we go. But we reach a point where you can't split the cells anymore, or it becomes very, very inefficient to split the cells. So you split the cell, you don't get a significant amount of capacity. So small cells, femtocells, picocells, microcells are one of the keys to addressing this huge demand for data. This isn't, of course, without challenges. These cells, all of different sizes, all of different powers, deployed in an organized manner by network operators, or even deployed in an ad hoc manner by individuals or businesses, only to interact together, still to provide good quality of service, the expectation of a good quality of service that the user has, and provide that capacity. And if not deployed properly, then you don't get the capacity, and we don't meet the 1000x challenge. Something else that was interesting from the presentation before lunch was the staircase that showed the increases in data rates as we evolve the technologies. And one thing that maybe you noticed, maybe you didn't, was that we're kind of reaching the edge of where we can get to in terms of spectral efficiency. The throughputs, bits per hertz, cannot be pushed too much further. We're already approaching the Shannon's limit, if you would like. So what can we do to increase the volume of data that we can push through a network without any increase in spectral efficiency? And by spectral efficiency, we mean the effectiveness of the receiver. Also, MIMO has been introduced. We saw that we go from 2x2 MIMO, 2 antennas on your transmitter, 2 antennas on your receiver. We go to 4x4 MIMO, 4 antennas on your transmitter, 4 antennas in your handset. And so we can increase throughput that way, but we can't go much beyond that. So although 8x8 MIMO is supported by the most recent LTE standard. So one way we can do this is by spectrum. Spectrum doesn't increase spectral efficiency, but if you have more spectrum, you can push more data through it. So you see this now with LTE, with carrier aggregation. That rather than listening to one channel, you might listen to 2 channels or 3 channels or 4 channels, all with different frequencies, all on different bandwidths of frequency as well. And then you aggregate that together to make the pipe fatter. So carrier aggregation is also important. We need to use more and more spectrum. We need to use licensed spectrum. Maybe we need to use unlicensed spectrum as well. And that's one of the areas that's currently under study with 3GPP, and something that Qualcomm and Ericsson are proposing is to use the 5 gigahertz spectrum for LTE as well as Wi-Fi, ensuring, of course, that the standard ensures those 2 technologies can coexist together. So we could use licensed spectrum, we can use unlicensed spectrum, aggregation of these different pipes to enable us to push more and more data through. Higher efficiency, those 3 things together will enable us to get to 1000x. Extra efficiency can be done at different points. We could use more efficient codecs, for example, for video, that would enable us to transfer that movie using less data. So that's also an important thing that needs to be considered. Okay, so densification, small cells is one way we could get to 1000x. The hooks are already here in the standards. So all of the standards that all of the network operators are using today already have lots of hooks to be able to do things like carrier aggregation, things like using your licensed spectrum for backhaul, or relays, range extension as well. So lots of this stuff is already defined somewhat in the standard, ready to be evolved and implemented and commercialized. Additionally, the vision here, of course, in this chart is that there's a proliferation of small cells across lots of different segments, whether they be residential or enterprise. And what we need to ensure, of course, is that these 2 worlds can coexist together. That ad hoc deployments of small cells can exist, peacefully. And peacefully, I mean without impact to the macro network that's controlled by the network operator. So this gives you some idea of what we will call an inside-out deployment of small cells. So this shows you some study that we did that shows you if you deployed about 9% of households with a small cell, and with an open small cell, that then provided some form of outside or inside-out type of coverage. This can give you about 500 times the current capacity that you would have, considering that area would be covered by a macro cell currently. If we take that up to 20% of household penetration, that gets us to 1,000x. Very simplistic model, of course. So you have to assume that these are deployed where the demand is. We need to ensure that these small cells do not interfere with each other. They do not interfere with the macro network. But this shows you the types of networks that could be built to meet this 1,000x challenge. And this was an example of where we tried to do this. And this was a hyperdense network that Qualcomm, along with the network operator Sprint in the US, and NASCAR, which is a form of US-based racing, motor racing, deployed what we consider is one of the densest LTE networks in the world at that time. So this was the garage area where the racing cars, as well as all of the pit crew, operate. Very fast-moving environment, very dense environment with a huge demand for data services. So you can see the dimensions here. This is 40 meters, so this is somewhat like 100 by 100 meters. And within that, we deployed 31 small cells to cover this area, and you can see the allocation of the small cells. You can see the distance in some cases between the small cells was very, very small. This enabled us to get about 40 times more capacity than they were used to getting in that type of environment. The aim of trying to do this, though, was to show that you cannot just deploy these in an uncoordinated manner. Well, they are deployed in an uncoordinated manner, but there needs to be coordination between them in terms of some self-organization. And so this highlighted some Qualcomm technology that's called ultrason. And ultrason enables the configuration of each small cell to be changed based upon what that small cell is trying to cover. So if that small cell is not covering anybody at that current time, we can switch it down, we can turn it off. By turning off the power, it doesn't radiate anymore, it doesn't generate any interference to all of the other cells. So as people move around, as the demand for data moves around, we can change the configuration of the network, both from a power perspective as well as a parametric perspective, to try to meet that demand and try to manage the interference between all of these cells. And this was a very successful demonstration. Another challenge with small cells is if a good example of self-organization, self-optimization, is if a user drove his car straight through here, and in a traditional macro network, every one of those small cells would have tried to hand off the call or the data session between each of those cells. That generates a huge amount of signaling, a huge amount of interference, a huge amount of overhead. So one of the ways we can do that is detection of fast-moving vehicles or fast-moving users, and then we don't do handoffs. We try to manage the handoff or even move it to a different layer. So this is the proof of concept, the type of small cells that we could see deployed. Very low power, very small form factor, low cost, and this would enable ease of deployment, ease of densification. But at the same time, we recognize that you need to have that self-organizing ability of these devices so that they can all coexist together, and all coexist together with each other, as well as with the macro network. I mentioned spectrum was the other thing. So we know that LTE, with LTE Advanced, supports carrier aggregation. Carrier aggregation is starting to be supported now in a commercial sense. A number of networks have rolled out carrier aggregation already, where we use not just a single carrier with a fixed bandwidth, but we use multiple carriers of different bandwidths depending on what's available. Currently, carrier aggregation is offered in licensed spectrum. So if an operator owns 2600 megahertz and he owns 700 megahertz, in a good example, he could take his 700 megahertz carrier and his 2600 megahertz carrier and use both of those or apply both of those to a user. Obviously, those frequencies have different coverage footprints, so all of that needs to be managed by the network as well. An additional component of this, which we could foresee, is the use of unlicensed spectrum to be able to do this. Unlicensed spectrum, 5 gigahertz is a good example where Wi-Fi is already there. Maybe cannot be used as the anchor layer because quality of service maybe is not predictable. The quality of service is not controllable by the operator and therefore not predictable. So we could use this unlicensed spectrum as secondary, supplemental type of carriers to enable us to try to get to increase this capacity. If the capacity is available in unlicensed, let's use it. If the device can understand that frequency, we can use it. Similarly, with the idea of shared license spectrum, this would be using spectrum that's owned by others or even the government, in this example in the US, at either certain times in the day or for a short period of time, whilst that spectrum is not being used by the owner. So a very similar type of concept to licensed spectrum, but the spectrum will be owned by others. All of these three things gives you more of that spectrum, enables you to try to meet this capacity demand. So this shows you the bigger picture of the idea of extending LTE Advanced in this example to unlicensed spectrum. So we have carriers of LTE between 700 to 3.8 gig, and these could be multiple carriers of LTE in multiple of the bands that are supported between 700 and 3.8. We use a supplemental carrier, possibly LTE in a licensed spectrum. The advantage of LTE in a licensed spectrum is it's arguably more efficient than Wi-Fi, so you would need less APs to provide the same amount of capacity. It's also more managed in terms of enabling a common core network to provide both of those carriers with a consistent approach to providing the data throughput. So summarizing, what we want to try to propose is spectrum is key. We need to use more and more spectrum, but we also need to use more and more cells, and we need to change the model that we use to deploy cells, moving away from macro cells, where your whole network would be cells of a very similar power, a very similar type of footprint, to use cells that very specifically try and target where the users are, and cells that very specifically try to manage the traffic that they carry, as well as optimize themselves so that they do not cause harm to each other. So spectrum, more cells, showing you that 1 + 1 can sometimes equal more than 2. So showing you really a similar type of concept where we can have all of the different technologies coexisting together and then try from the device perspective to manage these so that they're used appropriately when appropriately providing the user with the best quality of service. So in terms of what Qualcomm's doing to this, Qualcomm, of course, is a key contributor to the evolution of small cells, as well as providing silicon that goes in handsets. Qualcomm does provide silicon that goes inside of small cells as well. So we have chipset solutions for small cells. We are driving the push to find solutions to all of these challenges that we will face as we go to denser and denser networks, and this densification needs to be managed and handled and rolled out appropriately so that we can achieve the capacity increases successfully. That was small cells. The other thing I'll mention briefly is some of the other things that Qualcomm's working on, and this is labeled a little bit more forward-looking, creating the digital sixth sense. And this really shows, or tries to show, where we've come in the 20-plus years since mobility and mobile phones were introduced. Initially, we were there at the start, of course, with CDMA. We were there at the inception of the mobile internet. And now the smartphone, the way that we're all using smartphones, of course, it significantly changes our lives, and we're using them for more and more things. So a suite of initiatives that Qualcomm is working on to try to enable this evolution of the mobile, to try to do more and more beyond what we're doing now. So the types of things that we can do. Of course, all of this is driven by the Qualcomm Snapdragon processor that's inside of any phone that's powered by Qualcomm. Things like Qualcomm Talk, which is a reference design for a watch. And we've seen commercialization of that idea as well, where devices that you wear now will interact with your phone. In the case of the Talk, very clearly you can get alerts for emails, stock quotes, etc. on your wrist without going to your phone. Healthcare is 2net. So healthcare is a huge growth area with mobile wear monitoring of conditions, reporting back conditions to doctors of course is very important. Pictronics, Qualcomm Mirasol, trying to address the issue of the biggest drain on the battery of our devices. What's the biggest drain on the battery of our devices? Of course, the screen. So if we can make more and more efficient screens, it means that we can go longer and longer between charges. Qualcomm Vive is 11AC. So Qualcomm, of course, is heavily involved too with Wi-Fi as well. We have Qualcomm Atheros, and the commercialization of 11AC is what's covered by Vive. Location services, again, with ISAT, based upon not only traditional GPS, but also on using Wi-Fi to assist in location. So trying to do lots of initiatives, lots of businesses that help create this digital sixth sense. What that means in reality is we have to do all of this. And we can see from modem-based types of applications, carrier aggregation, we've mentioned already. Smart antenna tuning, envelope tracking, things that we can try to do that to address some of the challenges that we'll face as we build devices that cover huge frequency bands. If we consider now 700 megahertz through 5 gigahertz with 30 to 40 different bands that are defined by the standard organization that your phone should now be able to understand. Clearly lots of technology there. Similarly, computational cameras, noise cancellation, video, things that are associated with the way that the user views and sees data. So all of these things together, we need to consider as part of our smartphone. And I think that's all I have to say. So thank you very much for your attention.
Thank you very much, Kevin. I'm sure there are a lot of questions for you. They're making them over Twitter, so you will have enough time to answer them afterwards. But you said that the industry have to be prepared in the next 2 to 3 years for 1,000 more traffic. Is it correct?
I think We're not really predicting when that will happen, but going by history, we see that this type of number is not unrealistic. If you look at, I think AT&T said from the 5 years up to 2012, they were 200x increase in traffic. So
but you think it's possible?
Very much is possible, yes.
And well, you have explained how we're going to do that, but how you are going to do that, not me. But can you explain what do you think is going to be the leading technology for doing that? The most important technology for doing that?
So I mean, it has to be where we are now with 4G, which is LTE, and we're seeing the use of lots of different bands with LTE at the moment. So we have to continue the rollout, commercialization, and optimization of LTE.
And the thing is that this is kind of infinite. I mean, is it going to stop? No, you will always have to be preparing for the next 2 to 3 years.
Yes, correct. Yeah, I agree with you.
Okay,
Yeah.
so you have plenty of work to do.
Plenty of work to do, yeah.
Thank you very much, and well, keep in touch with the people in Twitter. They're asking you questions there.
Okay, thank you.
Very interesting, thank you. Gracias a Kevin.